Hello, my name is William DeRocco, and today I'm going to be talking about free-floating planets in the era of Roman. So before I dive into the meat of the talk, I just want to provide a bit of motivation for what I'm going to be talking about. I think everybody here has probably seen some version of this plot before, but for those of you who haven't, this shows the discovery space for the Roman Space Telescope, NASA's next flagship mission, which is set to launch in 2026. I'm sure you'll hear from Julie, we're still on track, so less than 2 years away. It's going to conduct a 5-year survey to detect planets with microlensing and is expected to detect several thousand exoplanets this way, including analogs of all of the planets in our solar system, with the exception of Mercury. So this is already something to be really excited about. I mean, this is soon, and I think now is really the time to gear up for it. But there's one aspect of this plot that I think is often overlooked, and it's the fact that this parameter space doesn't truly just cut off at 100 AU. Rather, it extends further all the way out to infinity, which is the domain of fully unbound objects. But there's a reason this isn't really often shown. It's that we don't really know what's out there. So sort of in keeping with the label that old cartographers used to use for the regions off the edge of their map, this parameter space to me constitutes sort of a kind of terra incognita for planetary demographics. However, in recent years, as probably a lot of you are well aware, we've just begun to explore this uncharted domain. Thanks to the tremendous decades-long efforts of the ground-based microlensing surveys like MOA, KMTNet, and OGLE, we've gotten our first few detections of the worlds that inhabit this parameter space. So what are these? Well, these are the free-floating planets from the title of my talk, or more colorfully, rogue worlds. These are the planets that are just drifting through the interstellar void, unbound to any stellar system. And our initial handful of observations from ground-based surveys have provided evidence that such worlds may actually dramatically outpopulate their bound counterparts. In the most up-to-date analysis of existing data by the MOA collaboration, which is shown here, they found a power law fit to their observations suggests that Earth-mass free-floating planets may outnumber bound terrestrial planets by more than a factor of 20 to 1, making free-floating planets by far the largest demographic of planets in the galaxy. Unfortunately, our current handful of observations provide really only a tantalizing hint of this population, but the details of it really remain unknown. But this will change with Roman. Roman's Galactic Bulge Time Domain Survey is expected to detect hundreds, if not thousands, of these worlds, providing us for the first time with the statistics necessary to begin exploring this vast, uncharted domain. And so there really are two primary questions of my research program that are driving what I'm working on, both of which I'm going to try to address in the remainder of this talk. Namely, what might be out there? What sorts of theoretical predictions do we have for this population? And then perhaps more importantly, what will Roman actually be able to see? What will we actually be able to quantify about these planets? So let's start with the first of these two questions, which is what might be out there? In order to start to predict what the FFP population might look like, we need to start by discussing their origins. This is still a large open question, and a large number of mechanisms have been proposed, ranging from star-like formation mechanisms, such as the direct collapse of gas clouds in interstellar space, to more planet-like formation mechanisms, in which the planet is formed initially bound in a protoplanetary disk, and then is subsequently ejected either by scattering off of some inner binary or by scattering off of another planet, tidal stripping, etc. But the key point here is that each of these different mechanisms imprints different features in the distribution of the masses and velocities of free-floating planets. So if we were to take these mechanisms and plot them in sort of an FFP mass versus velocity space, we'd end up with something like this. You can see here that each of the mechanisms is expected to lie in a different general region of this parameter space. So you can start to see why being able to reconstruct the mass function of free-floating planets would provide immediate insight into the relative contributions of their proposed origin scenarios. Now, look, this is just a cartoon that I made in PowerPoint. So if we really want to make predictions for what the population of FFPs might look like in this parameter space, we do have to rely on simulations. And there is a large body of existing literature on planetary ejection from which to draw. However, the majority of these studies begin with fully formed planets on fixed, often unphysical orbits. And so these fairly arbitrary initial conditions make it a significant challenge to actually connect the results of these simulations to predictions for a galactic population. And so this is where the work of me and my collaborator comes in. Our first results of which are finally to appear in MinRAS in a few days. Rather than beginning from fully formed planets, we ran 2,000 dedicated simulations that tracked the formation, evolution, migration, and ejection of growing planetesimals and planets in protoplanetary disks. Then what we did is we included a realistic distribution of different stellar system architectures in the galaxy, including single star systems, close binaries, wide binaries, etc., and then convolved all of these results to make sort of a first initial prediction for the mass function of FFPs in the galaxy that Roman might be able to see. And the really exciting thing about this work is that because we've run these simulations sort of from first principles, we can make a direct connection between planet formation theory and observable features in the mass function. But so your first question might be, okay, well, so how well does this all line up with the existing detections that we actually have of FFPs from all the ground-based observatories? And the answer is shown over on the right here, where our simulation results are these sort of blue dots, while the green and the red band correspond to the 2 sigma uncertainties from the most up-to-date FFP detections. And so what you'll see is that our results agree to actually a surprising degree, predicting a pretty similar power law to what's already been detected. But I really wish to stress that our results were in no way tuned to existing data. So we were pretty surprised to find that they aligned so well. However, this is just at the high masses. Below about an Earth mass is where we really start to enter this terra incognita, because at present, we don't really have enough observations in that window to probe what the mass function there would look like. But that's actually where things get interesting. And that's because we make a prediction for the mass function that significantly differs from a power law extrapolation to the existing data. We predict a dramatic decline in free-floating planet abundance below an Earth mass and a much shallower power law in the subterrestrial range. So this is already kind of exciting in its own right because it provides a clear target for Roman to go after. But even more excitingly, since we're able to connect each of these predicted features to underlying physical parameters in our models of planetary formation, if Roman can measure, for example, the location of this peak, it would provide immediate insight into the origins of FFPs and the underlying environments from which they come. So the takeaway of this first part is just that free-floating planets provide a really unique window into planetary formation and system evolution. And given that they may be the largest demographic of planet in the galaxy, there's something we really shouldn't be ignoring. Which brings us to the big question and the focus of the second part of this talk, which is, what can Roman actually see? And so obviously here's the catch, right? We want to measure the free-floating planet mass function, but as you all know, microlensing detections don't actually give you a direct measurement of the lens mass. What we ultimately observe is a magnification curve like the one that I'm showing here. And this light curve is ultimately kind of the only observable that we get. This is the primary observable that we collect. And so the duration of this magnification, is a degenerate combination of the lens mass, distance, and velocity in this case, something that I think pretty much everyone in this audience is familiar with. which means that on an event-by-event level, trying to estimate the mass of a single FFP is extremely difficult. Now, historically, since we've only had a handful of FFP events to work with, this was about as good as we can do. But Roman provides a solution. Its large number of detections will allow us for the first time to be able to leverage population level statistics rather than simply relying on event-by-event modeling. And so that's the premise of the work that I've been doing for over a year now. The first results of which I'm actually very excited to be able to share here with you today. Now, what I will say is that I'm still in the process of writing this up, and these should be considered very preliminary. They might change, but I think the broad features should remain largely accurate. But you might not want to take pictures of this or share this around. So what you're looking at here is the same contour you've seen multiple times through the talk now, showing the 95% confidence interval on the FFP mass function at present, as extracted from MOA data. What I'm about to show you is how this looks after 6 seasons of Roman's observations. With Roman, the uncertainties will reduce dramatically. If this power law extrapolation from MOA truly is the underlying mass function, then we will be able to reconstruct it to below an order of magnitude in uncertainty. But beyond this, Roman will also enable us to discover if the FFP mass function does not conform to this power law, as suggested by the simulations that I've been running. If, for example, we take that simulation prediction as the truth FFP mass function, we end up with this. And so clearly, the two mass functions are distinguishable statistically across a broad range of masses at well beyond, a 2 sigma level. And so the main takeaway here is just that by leveraging population level statistics, Roman will be able to start answering fundamental questions about the demographics and origins of free-floating worlds. And so with that, I'm just going to summarize briefly what we talked about. Currently, low-mass FFPs constitute, a real kind of terra incognita for planetary demographics. However, via dedicated ab initio simulations, we're able to start making concrete predictions for this population and connect features in its distribution to underlying planet formation models. Beyond this, though, Roman will be able to leverage its large number of FFP detections to begin doing population-level inference of the FFP mass function, and potentially reveal key features that really probe the origins of these enigmatic worlds. But as exciting as all of this is, there is still much more to do. On the theory side, we're working on extending our simulations to an even larger range of stellar systems and formation processes so we can provide more refined predictions for the population. Meanwhile, on the observation side, I'm continuing to really push to build this framework out for reconstructing the FFP mass function, maybe extend it to velocity space as well. There's also pushing a lot for joint parallax measurements that on an event-by-event level, we actually can get specific masses, which is super useful. Additionally, there's also the problem of false positives, which I really believe need dedicated work to understand if we want to be able to do any of this. And so I just want to end by saying that, I'm currently serving as the chair of the Free Floating Planet Working Group for the Roman Project Infrastructure team. And so I am always looking for people from the theory or observation side who want to get involved in all of this. I really believe that FFPs present an immense opportunity, but also an immense challenge. So if you are willing to strap on your boots and venture forth into this vast unexplored domain of planetary demographics with us, let me know. I'd be happy to chat with you. So with that, thank you very much. And I'll take questions now live, I guess.